Welcome to Maths Companion. In the last video, we have learned sequences. Let us remember what we have learned. A sequence is a group of numbers written in order according to a particular rule. And after that, we have seen that the sequence may contain any type of numbers. The numbers of a sequence can be natural numbers, fractions, decimals, or any type of numbers. Then we have seen that sequences can be made from different situations. We have made sequences from geometry, physics, and so on. Also, we have seen that sequences can be made from peculiarities of pure numbers, such as sequence of prime numbers. And lastly, we have seen that the same sequence can be described in different ways. We have discussed that for every sequence there is a rule. For every sequence, the term and their positions are connected. Let us find out the connection and let us try to express it with the help of algebra. Today, we are going to learn the algebra of sequences. Let us remember the sequences which we have learned in the last video. We have made sequences from squares. We have seen sequences of sides, perimeters, areas, and diagonals. Let me take the sequence of perimeters at first. Each number in a sequence is called term. Here 4 is the first term, 8 is the second term, 12 is the third term, and so on. And first term is denoted by x1, second term is denoted by x2, third term is denoted by x3, and so on. So we can say x1 is 4, x2 is 8, and x3 is 12. Now let us find the relation between position and term of the sequence. First term is 4, second term is 8, third term is 12, and so on. How the term and position is related? This is 4 into 1. Second term is 4 into 2. Third term is 4 into 3. So each term is obtained by multiplying 4 by its position. If so, what is the fifth term? 4 into the position, that is 4 into 5, that's equal to 20. Now what is the 20th term? 4 into the position, or that is 4 into 20, that is 80. Now what is the 25th term? Again 4 into the position, that is 4 into 25, and that's equal to 100. Now let us generalize. Let me take the nth term. Nth term is denoted by xn. What is meant by nth term? It is a term which represents all the terms of the sequence. When you put n equal to 1, we get x1, that is the first term. When you put x equal to 2, we get x2, that is the second term. So it is a single term which represents all the terms of this sequence. Let us try to find the nth term. We have seen that each term of this sequence is 4 into its position. So nth term is equal to 4 into, what is the position here? Nth term. So the position is n. So nth term is equal to 4 into n, and that is equal to 4n. So xn equal to 4n is the algebra of this sequence. And we can verify. When we put n equal to 1, we get x1 equal to 4 into 1, or 4. When we put n equal to 2, we get x2 equal to 4 into 2, that is equal to 8. When we put n equal to 3, we get x3 equal to 4 into 3, that is 12. Now let us take the sequence of areas. Again, let us try to find the relation between the position and term. First term is 1, second term is 4, third term is 9, and so on. How is the term and position related here? First term is 1, second term is 4. Here first term is 1 square, second term is 2 square, that's 4. Third term is 9, that is 3 square. So we can see that each term of this sequence is the square of its position. If so, what is the fifth term? Square of the position, that is 5 square or 25. What is the seventh term? Again, square of the position, that is 7 square or 49. What is the eighth term? Square of the position, that is 8 square or 64. Now let us generalize. What is the nth term? Again, square of the position, that is n square. So xn equal to n square is the algebra of this sequence. Again, we can verify. When n equal to 1, x1 equal to 1 square or 1. When n equal to 2, x2 equal to 2 square or 4. When n equal to 3, x3 equal to 3 square or 9. Like this, we can find every term from this algebraic expression. Now let us take the sequence of diagonals. Again, let us find the relation between the position and term. First term is root 2, second term is 2 root 2, third term is 3 root 2, and so on. How is the position and term related? First term is root 2, that is root 2 into 1. Second term is 2 root 2, that is root 2 into 2. Third term is 3 root 2, that is root 2 into 3. So each term of this sequence is obtained by multiplying the position by root 2. So what is fifth term? Again, position into root 2, that is 5 into root 2 or 5 root 2. What is seventh term? Position into root 2, that is 7 into root 2 or 7 root 2. What is eighth term? Position into root 2, that is 8 into root 2 or 8 root 2. Now let us generalize. What is the nth term? Position into root 2, that is n into root 2, and we can write it as root 2 n. So xn equal to root 2 n is the algebra of this sequence. Again, we can verify by putting n equal to 1, 2, 3, etc. Now, what is the algebra of the sequence of sides? It's very simple. The sequence of sides was 1, 2, 3, 4, etc. First term is 1, second term is 2, third term is 3. So definitely nth term is n. So in that case, xn equal to n is the algebra. It's very simple, so I have not done it here. Now let us take the second example which we have learned in the last video. The sequence of squares with sides 1, 1.5, 2, 2.5, etc. Again, let us take the sides, perimeters, areas, and diagonals. Let us find out the algebra of each of the sequence. First of all, let me take the sequence of sides. That's 1, 1.5, 2, 2.5, etc. Now let us find the position and term and the relation. First term is 1, second term is 1.5, third term is 2, fourth term is 2.5, fifth term is 3, and so on. Now you can see 1.5 is a mixed fraction. Let us convert that into improper fraction. How can we convert it? Let me take 1.5, multiply the denominator by 1 and add the numerator, and it should be divided by the denominator. So we will get 3 by 2. So 1.5 can be written as 3 by 2. Now 2, and how can we write 2.5? 2 into 2 plus 1 by 2 or 5 by 2, and then 3. So here we can see natural numbers and fractions. More clearly, fractions with denominator 2, 3 by 2, 5 by 2. Now let us express each and every term as a fraction with the denominator 2. How can we do that? How can we express 1 as a fraction with the denominator 2. One can be written as 1 by 1 or it can be written as 2 by 2. Now it's a fraction with the denominator 2. Then 3 by 2. How can we express 2 as a fraction with the denominator 2? 2 by 1 or 4 by 2. Now it is a fraction with the denominator 2. Then 5 by 2. Then what about 3? It's 6 by 2. Now each and every term is a fraction with denominator 2. See, all the denominators are 2. So in the nth term also the denominator is 2. So it remains unchanged. Now let us look at the numerators. For the first term, numerator is 2. Second term, it is 3. Third term, it is 4, and so on. Or when the position is 1, numerator is 2. When it is 2, numerator is 3. When it is 3, numerator is 4. When it is 4, numerator is 5. What is the relation? The numerator is 1 more than the position. So when the position is n, what will be the numerator? 1 more than the position. Means 1 more than n. How can we write 1 more than 1 in mathematical terms? 1 more than means plus 1. 1 more than n means n plus 1. So the nth term of the sequence equal to n plus 1 divided by 2. Here 2 is common everywhere, you can see 2, and the numerator is 1 more than the position. Now if you want, you can check. When n equal to 1, we get first term, that is 1 plus 1 by 2, that is 2 by 2 or 1. When n equal to 2, x2 equal to 2 plus 1 or 3 by 2. When n equal to 3, x3 equal to 3 plus 1 or 4 by 2, that is equal to 2. Like that we can find out each and every term from this algebraic expression. Now let us take the sequence of perimeters, that is 4, 6, 8, 10, etc. Here again we can find out the relation as we have done earlier. But we know one thing, that the perimeter of a square is 4 into the side. So the algebra of the sequence of numbers can be found by multiplying 4 by the algebra of the sequence of sides. Here, algebra of the sequence of sides is n plus 1 by 2, which we have found just now. Now simplifying 2 and 4, 2 2s are 4, so you will get 2 here. So that's equal to 2 into n plus 1. So xn equal to 2n plus 1 is the algebra of this sequence. Again we can check. When we put n equal to 1, x1 equal to 2 into 1 plus 1 or 2 into 2, that is 4. When n equal to 2, x2 equal to 2 into 2 plus 1, that is 2 into 3 or 6. When n equal to 3, we get x3 equal to 2 into 3 plus 1, that is 2 into 4 or 8. Now let us take the sequence of areas, that is 1, 2, 1 by 4, 4, 6, 1 by 4, etc. Again, the area in the square of the side. So algebra of the sequence of areas equal to algebra of the sequence of side square. That is n plus 1 by 2 whole square. We have seen that algebra of the sequence of sides is n plus 1 by 2. Now squaring, we get n plus 1 whole square by 4. So xn equal to n plus 1 whole square by 4 is the algebra of this sequence. Let us verify. When we put n equal to 1, we get x1 equal to 1 plus 1, that is 2 square. 2 square is 4. 4 by 4 equal to 1, which is the first term. Now when we put n equal to 2, 2 plus 1 is 3. 3 square is 9. 9 by 4. 9 by 4 means 2 4s are 8 and 1 remainder. So that is 2 and 1 by 4. Now when we put n equal to 3, we get 3 plus 1, that is 4. 4 square is 16. 16 by 4 is again 4. So this is the algebra of the sequence of areas. Now let us look at the sequence of diagonals. And we have already seen that the diagonal is root 2 times the side. So the algebra of the sequence of diagonals is equal to algebra of the sequence of sides into root 2. That is n plus 1 by 2 into root 2. So xn equal to n plus 1 by 2 into root 2 is the algebra of this sequence. So in these cases we can find out the algebra of the sequences easily like this. Now let us take another example. 3 matchsticks are used to make a triangle. To make an additional triangle, 2 more matchsticks are used. To make one more additional triangle, again 2 matchsticks are used. Now let us find out the sequence of number of matchsticks used. That is 3, 5, 7, etc. Let us try to find out the algebra of this sequence. For that we have to find the position and term and the relations. The first term is 3, second term is 5, third term is 7, fourth term is 9, and so on. Here first term is 3, or to make the first triangle we need only 3 matchsticks. To make an additional triangle, no need of 3 matchsticks, we need only 2 matchsticks. So it can be written as 3 plus 2. 3 for the first triangle and 2 for the additional triangle. Now 7 can be written as 3 for the first triangle and 2 for each additional triangles. There are 2 triangles, so 2 2's. Now how can you express 9? 3 for the first triangle and there will be 3 additional triangles. So 2 for each additional triangle, that is 3 times 2. That is, to make the first triangle we need 3 matchsticks. For each additional triangle we need only 2 matchsticks. So how can we find the nth term? For the first triangle we need 3. 3 is common in each term, and in the second term there is only 1 2. In the third term there are 2 2's. In the fourth term there are 3 2's, and in the fifth term there will be 4 2's. In general, in the nth term there will be n minus 1 2's. That is 1 less than n 2's. Or you can think in another way. To make the first triangle we need 3 matchsticks. To make each additional triangle we need only 2 matchsticks. So when we take n triangles, for the first triangle we need 3 matchsticks, and for the remaining n minus 1 triangles we need only 2 matchsticks. Now how can we simplify it? This is n minus 1 into 2 means we have to multiply 2 by both n and minus 1. That is 2n minus 2. So it can be written as 3 plus 2n minus 2. Let me write 2n at first. Then what remains? 3 minus 2. 3 minus 2 means 1 or plus 1. So that is equal to 2n plus 1. You can do this part in another way also. We have given that nth term is 3 plus n minus 1 times 2. What does it mean? 3 and n minus 1 times 2. Now 3 can be expressed as 1 plus 2. So it can be written as 1 plus 2 plus n minus 1 times 2. That is 1 2 plus n minus 1 times 2. So total how many 2's are there? N times 2. Lastly you can see n minus 1 2's, and before that there is one more. So altogether there are n 2's. So you can write n 2's, that is 2n plus 1. You can mentally calculate like this, or you can calculate like this. Whatever it be, the algebra of this sequence is xn equal to 2n plus 1. You can check when we put n equal to 1, the first term is 2 into 1 plus 1, that is 3. When you put n equal to 2, second term is 2 into 2 plus 1, that's 5. When you put n equal to 3, third term is 2 into 3 plus 1, that is 7. Now let us do some problems. First question, write the algebraic expression for each of the sequences below. Sequence of odd numbers. Second question, sequence of natural numbers which leave remainder 1 on division by 3. Third question, the sequence of natural numbers ending in 1. Fourth question, the sequence of natural numbers ending in 1 or 6. Let us find the sequence of odd numbers at first. 1 is the first odd number, 3 is the second odd number, 5 is the third odd number. So the sequence of odd numbers can be written as 1, 3, 5, 7, etc. Now let us look at the position and term and find out the relation between them. First term is 1, second term is 3, third term is 5, fourth term is 7, and so on. Let us look at the even numbers near to each odd number. 2 is the even number near to 1. So 1 can be written as 2 minus 1. Similarly, 4 is the even number next to 3. So 3 can be written as 4 minus 1. And 5 can be written as 6 minus 1, and 7 can be written as 8 minus 1. Now look at each of this. Minus 1 is common everywhere. So in the nth term is also the last part is minus 1. And what about the first part? When the position is 1, the first part is 1 into 2. When the position is 2, the first part is 2 into 2. When it is 3, the first part is 3 into 2. And therefore, when the position is n, it is n into 2 or 2n. So xn equal to 2n minus 1 is the algebraic expression of this sequence. We can verify by putting n equal to 1, 2, 3 and observing the first, second and third terms. Now let us look at the sequence of natural numbers which leave remainder 1 on division by 3. We have seen this sequence in the last video. The sequence was 1, 4, 7, 10, etc. Now let us write the position and term and find out the relationship. First term is 1, second term is 4, third term is 7, and fourth term is 10, and so on. Here we are dividing by 3. So let me look at the multiples of 3. 3 is the first multiple of 3. So 1 can be written as 3 minus 2. 6 is the next multiple. 4 can be written as 6 minus 2. 7 can be written as 9 minus 2, and 10 can be written as 12 minus 2. Now look at each of this. Minus 2 is the last part. So in the nth term also, the last part is minus 2. What about the first part? When the position is 1, first part is 1 into 3. When the position is 2, first part is 2 into 3. When it is 3, first part is 3 into 3. And therefore, when the position is n, the first part is n into 3 or 3n. So 3n minus 2 is the algebraic expression of this sequence. Again, we can verify by putting the values. Now let us find the sequence of natural numbers ending in 1. We have seen this sequence as 1, 11, 21, 31, etc. Let us write the position and term. First term is 1, second term is 11, third term is 21, fourth term is 31, and so on. The same sequence can be written in another way as the sequence of natural numbers which leave a remainder 1 on division by 10. So let me look at the multiples of 10. 10 is the first multiple, so 1 can be written as 10 minus 9. 11 can be written as 20 minus 9. 21 can be written as 30 minus 9. And 31 can be written as 40 minus 9. Now look at each of this. Minus 9 is the last part. Therefore, in the nth term also, the last part is minus 9. What about the first part? When the position is 1, it is 1 into 10. When it is 2, it is 2 into 10. When it is 3, it is 3 into 10. Therefore, when the position is n, it is the first part is n into 10 or 10n. So xn equal to 10n minus 9 is the algebraic expression of this sequence. We can verify this right or wrong by putting n equal to 1, 2, 3, etc. Now let us find the sequence of natural numbers ending in 1 or 6. We have seen this sequence also, that is 1, 6, 11, 16, etc. Now let us write the position and term. First term is 1, second term is 6, third term is 11, fourth term is 16, and so on. The same sequence can be written in another way as the sequence of natural numbers which leave a remainder 1 on division by 5. So let me take the multiples of 5. 1 can be written as 5 minus 4, 6 can be written as 10 minus 4, 11 can be written as 15 minus 4, and 16 can be written as 20 minus 4. Now look at each of this. Minus 4 is the last part. So in the nth term also minus 4 is the last part. What about the first part? When the position is 1, the first part is 1 into 5. When it is 2, first part is 2 into 5. When it is 3, it is 3 into 5. And therefore, when the position is n, it is n into 5 or 5n. Therefore, xn equal to 5n minus 4 is the algebraic expression of this sequence. You can verify by putting n equal to different values. Now the second problem, for the sequence of regular polygons starting with an equilateral triangle, write the algebraic expressions for the sequence of sums of inner angles, the sums of outer angles, the measures of an inner angle, and the measures of an outer angle. Let us first find the sequence of sum of inner angles. Sum of the inner angles of a equilateral triangle is 180, that of a square is 360, that of a regular pentagon is 540, etc. Therefore, the sequence of sum of inner angles is 180, 360, 540, 720, etc. Let us write the position and term. First term is 180, second term is 360, third term is 540, fourth term is 720, and so on. 180 is 1 into 180, 360 is 2 into 180, 540 is 3 into 180, 720 is 4 into 180, and so on. Now look at each of them. 180 is common, into 180 is common. So in the nth term also, the last part is into 180. What about the first part? When the position is 1, first part is 1. When it is 2, first part is 2. When it is 3, first part is 3. And therefore, when the position is n, the first part is n. So n into 180 or 180n is the algebraic expression of this sequence. Now let us look at the sequence of sum of outer angles. Sum of the outer angles is always 360. So the sequence is 360, 360, 360, etc. Now let us write the position and term. First term is 360, second term is also 360, third term is also 360, fourth term is also 360, and therefore the nth term is also 360. That is, xn equal to 360 is the algebraic expression for this sequence. Now let us find the sequence of the measure of one inner angle. One inner angle of an equilateral triangle is 60, that of a square is 90, that of a regular pentagon is 108, and so on. So the sequence is 60, 90, 108, 120, etc. Now let us write the positions and terms. First term is 60, second term is 90, third term is 108, fourth term is 120, and so on. Sum of the inner angles of an equilateral triangle is 180, and since there are three angles, it is divided by 3, and we have got one inner angle as 60. So 60 can be written as 180 by 3, where 180 is the sum of the inner angles and 3 is the number of angles. In the same way, 90 can be written as 360 by 4, where 360 is the sum of the inner angles and 4 is the number of angles. And 108 can be written as 540 by 5, where 540 is the sum of the inner angles and 5 is the number of angles. Similarly, 120 can be written as 720 by 6. Now look at the numerators 180, 360, 540, 720, etc. These are sum of the inner angles, and we have seen the algebraic expression of the sum of the inner angles is 180n. Therefore, the numerator of the algebraic expression of this sequence is again 180n. What about the denominator? When the position is 1, denominator is 3. When it is 2, the denominator is 4. When it is 3, the denominator is 5. What is the relation between them? The denominator is 2 more than the position. So when the position is n, the denominator is 2 more than that, that is n plus 2. Therefore, xn equal to 180n by n plus 2 is the algebraic expression of this sequence. Now let us find the sequence of the measure of one outer angle. One outer angle of a equilateral triangle is 120, that of a square is 90, that of a regular pentagon is 72, etc. So the sequence can be written as 120, 90, 72, etc. Now write the positions and terms. First term is 120, second term is 90, third term is 72, fourth term is 60, and so on. Sum of the outer angle is 360, and there are 3 outer angles for an equilateral triangle. So 120 equal to 360 by 3. The 360 is the sum of the outer angles and 3 is the number of outer angles. The same way 90 can be written as 360 by 4, where 360 is the sum of the outer angles and 4 is the number of angles. The same way 72 equal to 360 by 5 and 60 equal to 360 by 6. Look at the numerators. It is always 360, and therefore in the nth term also the numerator is 360. What about the denominator? It is 2 more than the position. So the denominator is n plus 2 when the position is n. So xn equal to 360 by n plus 2 is the algebraic expression of this sequence. Now the third problem. Look at these pictures. The first picture is got by removing the small triangle formed by joining the midpoints of an equilateral triangle. The second picture is got by removing such a middle triangle from each of the red triangles of the first picture. The third picture shows the same thing done on the second. How many red triangles are there in each picture? Taking the area of the original uncut triangle as 1, compute the area of a small triangle in each picture. What is the total area of all the red triangles in each picture? Write the algebraic expressions for these 3 sequences obtained by continuing this process. Let us first see how the triangle is formed. First of all, a triangle is drawn. Then the midpoints of each side is marked. Then they are joined and the triangle obtained is removed. Now there are 3 red triangles. The midpoints of each triangle is marked and the triangle obtained by joining them is removed. Now there are 9 red triangles. Again, the midpoints of each triangle is marked and they are joined to get a triangle, and those triangles are again removed to get the next figure, like this. So these are the figures given in the question. Now let us look at the figure one by one. The first question is, how many red triangles are there in each picture? In the first figure, you can see there are 3 red triangles, and each red triangle in the first figure is divided into 3 more red triangles in the second figure. So the total number of red triangles in the second figure is 3 into 3 or 9. Each triangle is made into 3 red triangles and there are 3 red triangles in the first figure. Now take one red triangle from the second figure. That is made into 3 more red triangles in the third figure. Altogether there are 9 red triangles in the second figure and each one is made into 3 red triangles. So altogether the number of red triangles in the third figure is 9 into 3 or 27. So we can write number of red triangles are 3, 9 and 27. Now the second question is taking the area of the original uncut triangle S1, compute the area of each triangle in the figure. We have taken the area of the original uncut triangle S1. Now in the first figure, the original uncut triangle is divided into 4 triangles, 3 red triangles and 1 white triangle, and they are of the same area as they are equal triangles. So one triangle is made into 4 triangles of equal area. Therefore, the area of one triangle in the first figure is 1 by 4. Now each triangle in the first figure is again divided into 4 triangles, 3 red and 1 white. And there are 4 triangles, each one is divided into 4 more triangles. So area of one triangle in the second figure is 1 by 4 divided by 4 or 1 by 4 into 1 by 4, that is 1 by 16. In the same way, each triangle in the second figure is again divided into 4 triangles in the third triangle. So area of one small triangle in the third figure is 1 by 16 divided by 4, or that is equal to 1 by 16 into 1 by 4, and that is 1 by 64. Now we have to find the total area of red triangles in each figure. We have seen that the area of one triangle in the first figure is 1 by 4. And there are 3 red triangles. So area of one triangle is 1 by 4. Since there are 3 red triangles, the total area is 3 by 4. Similarly, the area of one triangle, one small triangle in the second figure is 1 by 16 and there are 9 red triangles. Therefore, the area of one small red triangle in the second figure is 9 by 16. In the same way, the area of one red triangle in the third figure is 1 by 64 and there are 27 red triangles in the third figure. So the total area of red triangles in the third figure is 27 by 64. Now we have to find the algebraic expression of all these sequences. First of all, let us take the first sequence of number of red triangles, that is 3, 9, 27, etc. Let us write the position and term. First term is 3, second term is 9, third term is 27, and so on. Now 3 can be written as 3 raised to 1, 9 is 3 square, 27 is 3 cube. So everywhere you can see 3, the base is 3. What about the power? When the position is 1, the power is 1. When it is 2, the power is 2. When it is 3, the power is 3. So when the position is n, the power is also n. Therefore, xn equal to 3 raised to n is the algebraic expression of this sequence. Now let us take the sequence of area of a small triangle, that is 1 by 4, 1 by 16, 1 by 64, etc. Again look at the position and term. First term is 1 by 4, second term is 1 by 16, third term is 1 by 64. Now look at the denominators 4, 16, 64, etc. 4, 16 is 4 square, 64 is 4 cube. Now the square and cube of 1 is always 1. So the first term can be taken as 1 by 4 raised to 1. Second term can be taken as 1 by 4 raised to 2. Third term can be taken as 1 by 4 raised to 3. So everywhere the base is 1 by 4, and therefore in the nth term also the base is 1 by 4. What about the power? For the first term the power is 1, for the second term the power is 2, for the third term the power is 3, and for the nth term the power is n. Therefore xn equal to 1 by 4 raised to n is the algebraic expression of this sequence. Now let us find the sequence of a small triangle, that is 3 by 4, 9 by 16, 27 by 64, etc. Now let us find the algebraic expression of this sequence. Let us write the position and term. First term is 3 by 4, second term is 9 by 16, third term is 27 by 64. Look at the numerators 3, 9, 27, etc. 3, 3 square, 3 cube, etc. What about the denominators 4, 4 square, 4 cube, etc. So we can write 3 by 4 as 3 by 4 raised to 1. 9 by 16 as 3 by 4 raised to 2. 27 by 64 as 3 by 4 raised to 3. So everywhere the base is 3 by 4. What about the power? For the first term the power is 1, for the second term the power is 2, for the third term the power is 3, and for the nth term the power is n. Therefore xn equal to 3 by 4 raised to n is the algebraic expression of this sequence. Today we have learned algebra of sequences. In the algebra of a sequence, the relation between the position and term is given with the help of algebra. Substituting the value of n in algebraic expression, we can easily find the terms. Now, I am going to give you an assignment. Write the sequence obtained by adding two adjacent consecutive terms in counting numbers starting from 1. Write the algebraic expression of this sequence. In every question you can do something. Sometimes you can do it fully, sometimes you can do half of it, sometimes you can do at least one step. Try it. And if you are not able to do it, means don't worry, you'll get the answer in the next video. Let me express my sincere thanks to my friends Naufal sir and Sudhakaran sir, who have given the suggestion to give assignment at the end. Hope you are all doing well. I'll be back with another video. Till then, bye.